Hi there everyone, how are you? So today we are going to discuss a new kind of system design research problem which is YouTube video search. And what the problem goes as follows that sometimes like a interviewer may ask you to design a kind of YouTube video search system. And what happens is that you go to a website and you are asked to build a system where sometimes you will enter a text. So in this case, like you enter playing guitar at night, and then the system should return the search results of the videos which satisfy this constraint. So it will actually output videos of a person playing guitar at night in a decreasing order of relevance. So your job is to build like a system in which you can send a text as input and output comes like a ranked list of videos. So this is like different from the earlier video which we covered, because here like the input is text and the output is videos. So here is a typical conversation which can go on between a candidate and interviewer, and this is how like you can actually ask an interviewer about the requirements. So for example, like a candidate can ask the interviewer that okay, so is the input on the query text or whether a user can search with an image or video. So since here we are focusing only on text, so the interviewer will say that the system you're trying to build is actually operating only on the text. And then sometimes like the candidate might say that the content on the platform, is it only in the videos forms or in other kind of forms. So in case of like YouTube, like it's mostly videos, so the content which you can recommend is mostly videos. So that's why like the interviewer might say that okay, the platform only serves videos. Okay, good. So now the other point is that okay, so now sometimes like a candidate might ask the interviewer that is the training data available, and the answer is that okay, you have like a video and you have like some data which is associated with the video, and you have like a text query which is basically what allows that video to be pulled up. So for example, let's say you are searching, let's say you have a video of a dog playing in a basketball court. So then you will have like the video of the dog, and then you also have like a text query which says this is video of a dog playing in the basketball court. So you have a video and then you have a text query which is actually explaining what the video is about, and that is like a data set which you can assume, and that is what the interviewer allows you to do. So now the other point is that the candidate can clarify that what is the other type of language which we can support. But since like most of the people in the world speak English, so the interviewer can say that only English is supported. And the scale of the problem is basically that you have like around a billion videos which you actually want to recommend. So in our case, like for example, if you enter a search query in the text box and there are a billion videos which you actually have to compare against, so it will be actually like a very slow operation. So that is something which you have to keep in mind while making a system design like this. And the other question is that is personalization involved or not. So generally like YouTube personalizes the information for you. So if I enter a query and you enter a query, obviously it will look at the past history of what we watched, and then it will suggest the content accordingly. However, for the purpose of this problem, the interviewer will say that no personalization is required. So your conversation can vary with the interviewer, but in general, this is like the flow it should take. And then once you are done, you can actually summarize the problem statement which you are trying to solve. So in our case, like we are trying to design a search system, and basically the input is a text query and the output is a list of videos that are relevant to a text query. So then you can draw like a particular diagram which talks about like what is the input and output of the system before actually going into the architecture. So we want to build like a pipeline, and what happens, so this pipeline is known as video search system. And what happens is that you are given a text query, for example, dog playing indoors, and then output is like the results which are like recommended according to like which videos match this. So now um, okay, so now there is like so there are like two types of ways in which you can solve this problem. So for example, let's say you entered a piece of text. So let's say you entered a piece of text like this. So obviously you have like so YouTube, let's say you have a lot of videos, video 1, video 2, and so on till video 3, and so on till video n, and you have like a corresponding textual description for each video. So you have like a textual description for each video, and you have like a incoming text. So let's say you have an incoming query, which in this case I call as q. So the way like you can retrieve like a relevant video is that you can compare like this query with all the possible texts which are like the text description of the videos. So here, like for example, it is t1, t2, and so on till t4. So you can compare this query, and that is something which is known as a text search. So once you rank like all the videos which match your textual query, then you get like a ranked list. So let's say that this list ranking is rank 1. And then there is another way in which you could do this problem. The other way is that you actually look at the actual content of the video. So you build like a kind of system in which what happens is that you have like an input text, which is the same text here, and then you actually compare it with the content of the video. So if you have 4 videos, v1, v2, v3, and v4, so you actually somehow look at the content of the videos in the visual space, in the pixel space, and then you are trying to match whether that video is matching the input text or not. So so this would be important, for example, if a user uploads a video which has no text description. So in that case, if you build like some sort of system which is able to ingest the video and understand what is happening in it, then you can actually compare that video with the incoming text query. And obviously, since like we don't have like the textual description of the video, so in this case like the comparison will happen between our input text and all the actual video content which is present on a platform like YouTube. So let's say that you conduct this type of search, which is known as a visual search, and you end up with another ranking called R2. So as you can see, there are like 2 pipelines here. So one is the one in which like you do text-based comparison. Another one is the output of the visual search. And you combine like these output rankings of the 2 videos, and then finally you end up with a final ranking, which is what you are concerned about. So now let's take a deeper look at what the visual search system looks like. So it is like pretty clear that in a visual system search, your network will look like something that you have like a input video, and then you have a query, in this case dog playing indoors. So your network will be like any ML model, and what you can do is basically you have a separate video encoder which encodes like the video and gives you like a video embedding, and this video embedding in general is like some vector representation. And similarly, you feed forward like your text query, and then you get some text embedding, and you can compare like this text embedding to several video embeddings. So you have like video embeddings v1, v2, v3, and so on v4, and you can compare like the text query, which is q, with all of these embeddings, and you can basically understand which one is more similar to the input video. So like v1, v2, v3, v4, you can evaluate which one of those is most similar to q, and then you can rank them accordingly. So the other thing is, for example, how do you conduct like a text search? So let's say you don't want to look at videos at all, but like you for a video, you basically know like what it is, its title, and like what are some corresponding tags associated with it. So whenever like a user uploads a video, he is actually giving it a title, and then sometimes like he gives it a tag. So what is like the correct way in which you can use this information? And that is something called text search. So whatever your input query is, you can search for all the videos titles in your inventory to see like which kind of videos match those. So for example, here if your network contains like dog playing indoors, you can obviously search for, okay, dog playing indoor is present in one of the videos, and since like all the 3 words are present, that is actually like a very high recommendation. Similarly, if you look at this video, it only contains dog and enjoyed and then in our house. So The problem is that in this case, like you can see, if even if like you do a word based search, so if you have 10 videos and you have text of all those videos and you try to search the input words in those videos, it will only work as long as the title of the video you are looking at has the exact word. So in this case, if you look at this video, how our dogs enjoyed the last night in our house, so it does not contain the word play, and it does not contain the word indoor, but then you know that the dog is actually playing, the dog actually enjoyed the party, so it is like actually playing, and it is in their house, which is actually indoors. So even though like this textual query is relevant to this query, but if you are trying to do word search, like you're trying to search the word between the exact word playing and indoor in this type of title, it will actually not come up. But like the meaning wise, they are actually the same. So obviously you can imagine that this kind of text search would not work that well. Okay, so now that we have described like our the way like our model will work from a broader perspective, the third thing we need to talk about is basically how will our data preparation look like. So in data preparation, it is pretty simple because the interviewer told us basically what we are given, and the data is essentially that we are given like the content of the video, which is like the file name, and we are given like a description, we are given like a description of it, which is like some, so it's a description which is generally provided by the person, or it is provided by someone. So let's say you are a user and you uploaded a video, then there are two ways you can get the description, right? You can basically, as the person who uploaded it, you can put the description in the description box which is appearing below the video, or you can also there is another way is that so if there is like a person who is speaking in the video, you can extract his subtitles, and then from you can feed those subtitles to some sort of model, some sort of machine learning model, and you can actually try to summarize what is happening in the video. So this is the way like you can look at all the videos and try to summarize what is happening, and this requires some sort of AI. But for any sort of video, like you can actually understand, you can actually build like this sort of queries in it, which is this. So in this case, like the assumption is that all the videos will have like a unique query which is associated with them. So for example, there is only one video in which like they are celebrating graduation. There might be other videos also, but here that is the assumption. So you are given videos, you are given a lot of queries, and then your job is to actually then you split it into like training set and a validation set and a test set, and you can train your model on this kind of data. The next thing is, how do you design good features which can actually help you in building such kind of recommendation system for videos. So a good, so obviously you need to build a model which can take like these queries as input and convert them to numbers in order to feed it to the model. So let's say that you are given like a query like a person is walking in the Montreal. So sometimes in NLP what happens is that you are given things which are like, so here like you can see there is a special kind of punctuation in E, and then there is some words which are like capitalized, and so a model will have like, there is like an infinite variation which can come in a natural language, because some words may be capitalized and some might not be. So how does like a model make sense of it? So one step which happens in NLP is that you try to like convert all the videos, all the input text into a single normalization. So you try to like lowercase it, and then you try to, the next step is tokenization. In tokenization, what you do is you take your input sentence and you break it into corresponding words. So in this case, for example, you have like a person walk in Montreal. So your model is basically something which knows beforehand like what all possible words can come. So it is having, so let's say in English language there are 20,000 possible words. So your model will need to know beforehand that any word which you input into it will be one of these 20,000, and this is something which we call as vocabulary. So the aim of the tokenization procedure is actually to convert the input sentence into the words which are actually present in the vocabulary. So in this case, we assume that the tokenizer broke the person into something. It broke this whole sentence into the words which were actually present in the vocabulary. So these individual words like a person walk in Montreal were actually present there. So what happens in case, let's say, a word is not there in the vocabulary? So let's say you make like a nonsense sounding word like person ghoulish. So in this case, like, there is no word called person ghoulish, but then if you actually split this word as person and a ghoul and a ish, so you can see that these three words, person, ghoul, and ish, are actually words which are actually present in the vocabulary. And the tokenizer's job is to understand like how it can split like a given sentence into the words which are guaranteed to be in the vocabulary. So one extreme case is, for example, sometimes you are given a word which makes no sense. Let's say you're just given a random permutation of letters, and this is something which is like not even present in the, which is like, so there is no word called BCA BAC in English language. So in this case, how will you tokenize it? So the worst way for a tokenizer to work is basically it can separate all of these input words in this whole word by characters, and it can feed like individual character to the model. So in this case, the word is 1 2 3 4 5 6 words long. So in this case, you can actually feed 6 separate words to the tokenizer, and you can feed like these 6 separate words to the model, and it is like absolutely guaranteed that since like a word at the fundamental level is made of a character, it sort of reasons that a character at least will be present in the vocabulary. So you can understand that there is like a trade-off going on here in the tokenization step, and the trade-off goes as follows. So for example, if your given word is made up of some words which can be broken down into like well-known words. So coming back to the example of person ghoul, in this case you can break this word as person and ghoul. So in this case, it will only be 2 words which you can feed to the model and then get your answer. Or another way to break this would be to break it in terms of characters, to break it in terms of individual characters. So here, when you break it in 2 words, there are only 2 words which you broke it to, and here, and if you try to break it by characters, you will break it into each individual word. So the length of the input sequence to the model will actually grow, and in this case, the length of the input sequence will actually be less. So a good tokenizer will be something which can break your input sentence into the words which don't into words which make sense and then are present in your vocabulary, and it gives you like the minimum possible size which you can inject into the network. Because if you inject like some very long input sequence to the network, then obviously it will consume like a lot of flops, because flops directly depend upon the length of the input sequence. Okay, so coming back now, let's say that your model has actually taken these words and it has broken like the words into individual integers, which is 33, 28, 4, 16, and 99 here. What is like the next step which you do? So generally what happens is that you have like, so since the machines cannot understand language, right? Because all you can do in a neural network or in any sort of machine is basically just represent the things as numbers, because we are on a 64-bit machine and we need a way to convert like the words into numbers. So you can imagine that you can build like a lookup table, a sort of lookup table beforehand, and what it does is that for all the possible words in your vocabulary, you have already sorted them and you know that what is their ID. So if you build like this sort of lookup table beforehand, so this is like your vocabulary in which you feed it all these words, and then each word is indexed into the ID. So then given a sentence, you can actually construct like a integer sequence on it. So for example, you have an input word car. So then you can directly go into this vocabulary and you can look at, okay, car, what is the index of car? Is it is 128. So you can feed like this integer 128 to the model, and it will somehow understand that this 128 actually corresponds to car, and then it can actually perform its computation. Now, there is one other way in which like you can convert your tokenized inputs into the there is one other way in which you can convert your tokenized inputs into a proper kind of numbers, and that is using a hash function. So what a hash function does is that uh, so let's say your vocabulary has 100 words. So what you can do is like as soon as you encounter a word, you can pass it through a hash function which gives you like some integer, and this integer is the actual number which you feed to the neural network downstream neural network. So you can imagine that in this case, in the case of lookup table, you had to store beforehand what is like the correspondence of each word to a particular integer, and this requires storing the entire vocabulary in the memory, and it does not work. So for example, like if you have to store the entire vocabulary in memory, it will take a lot of memory. The other way is that you are having some sort of hash function which is looking at these input words, and then what happens is that this hash function can operate on any of the input words, and computing hash function is really fast. So in this case, you don't have to build anything in memory, because as soon as you see a word, you can directly hash it and compute its integer. But the problem is, because hash function is computed for every time you see a word, it is going to be a bit slower than keeping all of this whole data structure in memory, and this would be like a pure this would be like a very slow mechanism. Now another thing which you can imagine is, for example, let's say this whole if you are storing if you're using these two techniques to store an input word, and let us say that you encounter a word which has never been seen, you encounter a new kind of word which has not even been seen during training. So let's say you encounter a dog, and the dog is not present in your vocabulary, and so how could you handle it? So one way you could handle is that your tokenizer actually breaks it into DOG separate characters, and it is guaranteed that these characters are present in the lookup table. Or the other way is, let's say you have dog. So obviously the dog is not present in the vocabulary, and you cannot add like a new word to the vocabulary due to some reasons which I will talk later. But what you can do is, like, it is guaranteed that any hash function will be able to operate on a given word, even if it's not in the vocabulary, and it will be able to actually map it to a particular integer. So in this case, like, since hash function is guaranteed to map it for any unknown word, that is like a really good thing, and you can use the hash function to build this property in your network. So overall, like, out of these two approaches, what you should do, like what you should use, people have tried using lookup table. So this is the best way on which like the transformers of today rely upon, and that is something which is recommended by all the good folks like who are implementing transformers right now. Okay, the next thing is, how do you, so since you are inputting like video to your system, how do you actually prepare that video data? And this is like a very important bottleneck which generally comes up in system design. So a normal person will say, okay, that you build like some sort, since like a video can be very long. So if you have like a so let's say you have 1 minute long video, and it is shot at like 60 frames per second, then the number of frames you have is like around 3600, and there is no model in the world right now which can process these 3600 frames together in the memory, because generally their memory blows up. So the correct idea sometimes is that you take the video and then you decode it, and then it gives you like all the 3600 frames. But instead of actually sampling all the 3600 frames, you try to sample some of the frames which are like very really important. And obviously you could imagine that you can a video has a lot of redundant information. So for example, if it's capturing like 60 frames per second, obviously like a lot of the things don't move in 1 second only. So then you can get away with only like sampling the video at 1 frame per second, in which case like it will drop to 60 frame input. So you can find like smarter ways to sample. And another thing is that sometimes a video contains a lot of duplicate content. So for example, let's say in the first 30 minutes there is an object which has not moved at all, and then there is an object in the last 30 minutes which has started to move very fast. So obviously you want some frames in the initial 30 minutes. Since they are pretty much similar, you can sample only some frames, but later on, once it is in motion, you can sample like a lot of frames. And then you can construct like such sort of samplers. There is a lot of work on how such type of like temporal video samplers, which like actually adaptively sample frames, can be done. But the key point is that you can't process the whole video, and you try to sample some of the frames, and then finally you resize them, because these videos are generally like 4K, and a good type of network generally processes like 1080. To the best of my knowledge, like a good network these days only processes like 1080p by 1080p videos. So because like 4K or 1080p doesn't make that much difference in the model's performance beyond like a particular limit, and lower size is actually easy to process. It won't consume as many flops. And then you resize your, so once you have like resized your video, you can pre-process your data and then finally save your frames as a numpy file. So now here there are two trade-offs which I want to talk about. So if you look at the bottleneck of the system, the biggest bottleneck lies in the decoding frame, because generally what happens is that a video is stored as a MP4 and it is not possible. So if you want to like go to frame 10, it is not possible to decode frame 10 until you have decoded like frame 1 to 10, and the decoding is generally taking a lot of time. So if you try to build your data loader in such a way, then in which like you're trying to decode frames on the fly, then you will see that your process becomes CPU bound, because your thread tries to like spend a lot of time decoding all the frames of the video. And obviously you can't keep all the video frames in memory, because like a 1 hour long video will, if you try to just uncompress it and save each video, then save each frame, it will blow up to maybe like a 80 gig. So a 1 GB video can blow up to 180 gig, and that's not good for the memory. The other point is that so this is a trade-off which you have to make. So luckily there are some libraries like NVIDIA DALI, and what they do is they allow you to decode the video using like the cores of a GPU instead of decoding on the CPU, and that actually results in immense amount of speed up. So while you're writing your data loaders for video, make sure that you are never dumping frames to the disk, because this is a really bad practice. And the other thing is that you should never so you should rely on something which decodes the video on the fly, and you can look into these libraries which I talked about to get like good information. So this is a thing which traps many candidates, and this is why a lot of video pipeline fails in practice. So this is not similar as image kind of networks where you can get around with just saving one image, but in video you decode on the fly. The other thing is that so in model, so we have discussed like how we can process the video. Now let's talk about what will our model look like. So the model will look like, so the model will have like two parts to it, and we have discussed this before, in which case like for a given query, like there is like a text encoder, and then there is a video encoder, and then you are somehow trying to compute like the similarity between the two. So what is like the architecture of a text encoder? So let's first discuss like how do we encode text, and then we will talk later about how we can encode videos. So in case of text encoder, it is like a generic block. What it does is it takes like input as a text query, and then finally it outputs a vector of numbers, and these numbers somehow contain like a higher dimensional representation of your whole document or your sentence and whatever you care about. So the key point is, how do you go from this sort of input to the output, which is a number? And there are two ways in which you can get about it. There are two ways. So there is one way which is known as the statistical method, and then there is another way which is known as the neural network way. So first I will talk about what is a statistical method. And one of my friends actually got rejected in Amazon because of this, because he didn't know this concept, and it is like very easy. So for example, let's say you are given a sentence. So you are given like multiple documents, you're given like multiple sentences, and you want to convert your sentence into numbers. So one naive way you can do is that you can count how many times each word is occurring in the sentence. So for example, here this person is nice, very nice. You can see that nice occurs twice, so your nice count is 2, and then your is basically once. So you can construct like these sort of count, and this is like a frequency based counter. In this, the size of the frequency, so the number of unique elements in this vector is basically the size of your vocabulary, and each of the items here can tell you like how many times a particular word has occurred. So you can see that there are two problems with this approach. First is that if your vocabulary is very large, so let's say if your vocabulary is maybe 30,000 words, then each of the input sentences will have a 30,000 vector associated with it, and most of the entries in it will be zero, because generally, like when you read an article or if you look at some document, it doesn't contain like a lot of words in the English language. So this would be like a very sparse vector which contains like 30,000 elements, and there is no way you can like store like all this information, because if you are most of those numbers are sparse out of these 30,000, then you are not really doing a good job, and you could get away with maybe constructing some sort of representation which is dense, which doesn't contain all values of zero. But how do you do that? That is a matter for the next thing, which I will talk about. Now the other thing here is that the other limitation of this approach is that it does not take into account like it doesn't take into account the relative order of the words. So for example, let's say you have this sentence, today is holiday, and then you have another sentence called holiday is today. So in this case, like the sentences, like the order of the words is actually lost if you are just counting like the mere number of words in each sentence, and you are not concerned with the ordering of the words. And this is actually like a big blunder, because it is actually not able to it's not able to capture some fine grained nuances which are not there at all. So this is like one other problem with the bag of words approach. Now there is another problem which comes, and this problem is something known as the problem of repetition. So generally, like statistically, what happens is that sometimes in your words, when you are speaking sentences, there are a lot of words which appear many times. So for example, the words like oh, the, is, these are like prepositions which come many times. So if you take like multiple documents in which these words appear many times, then obviously like when you will construct this vector, you will most of the times find that the value corresponding to is like pretty high, maybe that is 100, and all the other values are pretty low. So what will happen is that if you have like some words which are very common and they occupy like a very large weight, they will try to overwhelm all the other numbers which are present in this vector, and that is not really good, because in that case what will happen is all your network will learn is to identify the words which are very frequent in the vocabulary, and it will like not able to distinguish between the words which are pretty low in the vocabulary. So what we want is like some sort of representation where we keep this frequency thing, but we can downweight like the words which are statistically more likely, in order to reduce their impact, because we want the network to understand all the words equally. So this was like a problem which was solved by uh, TF-IDF. And what is its key idea? So the key idea of TF-IDF goes something as follows. So let's say that you have two sentences. One sentence is today is holiday, and let's say there is another hypothetical sentence is. So while you are computing like the while you are computing like the vector for this sentence, then what you will do is like so today appears once, is appears once, and holiday appears once. But you know that is appears many times in in multiple documents. Like for example, here it appears 3 times, here it appears 2 times, 1 time. So you generally don't give that much importance to the word is because it's naturally very high frequency. So you want to somehow reduce the weight of this one. And how will you reduce that? So you calculate like a additional term which is known as inverse document frequency, IDF. And how you do that is basically you take like a log of what is like the total number of documents which are present here. So here like you can see that there are two sentences present, and then there is, and how many times like your is occurs here. So here is in total is occurring like 4 number of times. So it is like occurring 4 number of times, and this is like a term which you multiply with the frequency of is. So your resultant value becomes something like log 2 to the base 4, and that is what you are searching for here. Okay, so once this is clear, so the key point is that you're calculating it in such a way that you can downweight the is. So the resultant vector which you will obtain for this sentence, which is today is holiday, it will have higher value for today and holiday and a lower value for is. Not because although these words have occurred once in this sentence, but today and holiday are some words which don't occur many times, so that's why they have a weight of 1. And is occurs many times, so you don't want the network to learn that much. It doesn't hold that much relevance to the input, so you keep like, so you reduce like this count of weights on the amount of weight assigned to is. The next, so the problems with TF-IDF are still what we know. So which are the original problems in bag of words, which is basically that you need to pre-compute the term frequencies. So if you have a new sentence, then you need to count how many times each word is occurring, and for that maybe you will use some sort of hash table or something, and that will consume like a lot of memory and also like time, which is linear in terms of sequence length, because you will have to go through the entire sentence to find the words which match. And the however, like since this is still frequency based, it does not contain like the order of the words, and also the representation is still dense because it has the its size is basically the number of words in the vocabulary, and most of those will be zeros. And if you have a 30,000 dimensional vector, obviously you don't want to process that. So is there another way, in which like you can process it? So there is a way which is known as machine learning based method, which is that instead of trying to construct like the embedding vectors by hand, you somehow try to learn them. And the idea is that instead of having like a 30,000 dimensional vector, most of whose entries are 0, maybe let's say you are only learning a 1024 dimensional vector for each word, and none of those entries are 0. So it's like a pretty dense vector, and it contains like a lot of information about what the word is. So let's say you are given 2 words, maybe one of the word is tweet and one of the word is Facebook. Now obviously if these 2 words are having 1024 dimensions, there is no way to visualize them because we are humans and we only look at the words in 3 dimensions, and in books if we are studying it's 2 dimensions. So if somehow like you come up with a way to reduce like this 1024 dimension into 2 dimension for the word tweet and for the word Facebook, then you can actually plot them. And let's say you have a ML model which can convert a word into this high dimensional representation of 1024 dimension, and then you reduce it and you are looking at the words. So what you will find is that there are techniques in which the words of similar meanings are actually closer to each other in the embedding space. So here like you can see this whole cluster is of the vehicles. It's all sort of like vehicles which drive. This is like all foods, and this is like all the social, these are like all the social media things which can happen. So now how do you actually learn? So the problem boils down to how do you actually learn a ML model which can go from like a input to an output vector which you are looking for, which is like a high dimensional vector, maybe like a 1024. So how do you convert like a word into this 1024 dimensional vector? And that is like a key question. Okay, so how do you do that? There are two ways in which you can do that. One is called like what. So the most classical way in which you can do it is, let me just clear this. Okay, so the most classical way in which you can do this is something called an embedding table. And what embedding table does is that let's say you have 2000 words in your vocabulary. So you assume you have 200 words in your vocabulary, and you assume like a matrix whose number of rows are 200 and whose number of columns are the dimensionality of like the vector you're trying to learn. So let's say that each of the word you want to learn is having 1024 dimensions. So in this case, like you can imagine that each of the word does, work, or whatever is associated with some random 1024 numbers which you don't know what are they. Okay, so the point is that if you initialize this matrix of 200 by 1024, then each row corresponds to a word, and all of these are like 1024 dimensional, and these are like some numbers which make no sense, and you want to somehow make these numbers resemble the word. In this case, you want to resemble these 1024 numbers to represent the word does. So how do you come up with that? And so that is like an idea which is known as Word2Vec, which was a seminal idea which was actually published by Thomas Mikuloff. And I'm not sure if Jeff Dean is on the paper, but the key point is that it came out of Google, and those guys are really brutal, and they come up with like interesting ideas all the time. So that's why like I have a huge amount of respect for them. So what does Word2Vec do? So assuming like you understood, like we have like this giant set of metrics with the words and the number of dimensions in it. Somehow we want to learn this matrix, and there should be like some sort of supervision algorithm or some sort of learning objective which allows you to do that. And turns out that it is pretty simple. And what the idea is, so the idea is pretty simple. So let's say that you're given a sentence called how to make a pizza. So what you do is that you actually center. So in this case, like you have a sentence how to make a pizza, and what you're trying to do is that you want to predict like the center word make by looking at the words around it, which is like how to make a pizza. So what you will do is that you will feed like these words which are the neighboring words, how to, pizza, and at, and then so by looking at this information, you are actually trying to reconstruct that you're trying to predict like what will be the center word. So in this case, the center word will be make. Okay, so you can imagine, let's say your document has, let's say, 1 million words. It's like some novel or something, so it has like 1 million words. What you can imagine is that you can pick like these different size windows. So you can pick like these 5 windows, different 5 size window, and you're trying to predict like the center word given the context of surrounding word, four surrounding words around it. So in this case, this is 5 sentence word. There is 2 words on the left and 2 words on the right, and you're trying to predict you're trying to predict like the center word. So you can imagine that you can train this type of network on all the text in the world, and this does not require like any labels, because you already have like a lot of text written. So you can just choose like a subsequence of the text, and you can just try to predict the center word, and you already know that. So this is like a very interesting idea, and this is really powerful. And it is really powerful. And why is it powerful? So first of all, what goes on behind the scenes in this Word2Vec is something which I will describe now. So basically, let's say that you have W words, and you have W words, and you are trying to learn a matrix of D dimensions. Okay, and let's say you are given an input of size L, out of which there are L-1 words which are fed to the network. So in this case, like how to make a pizza, there are like 5 words, and since you're predicting the center word, you are trying to feed the 4 words into it. So the number of words which you actually feed to the network, the L, the sequence length, is actually um, is actually 4. Okay, so for so once you feed these words and you're trying to predict like the center word. Okay, so that is how it looks computationally. And yeah, so you can process that. So in this case, like for example, if you are predicting the word, if you want to feed some number corresponding to word how, you will look at your word matrix which is of size w cross d, and you will find the index which corresponds to how, and you will find its d-dimensional vector, and that's the vector which you will inject into this network v1, similarly v2, similarly v3 and v4. So you will try to inject these networks, these vectors, and try to combine them in such certain way, and then finally you will end up with like something which is giving you another vector v5 dash, and you want this vector to be actually the word which is the word make. And how do you get that? You can actually multiply this vector v5 v dash, whichever whatever the network predicts. Let's say this is of d dimensions. You can try to multiply this vector which is d dimensional by another vector called of dimension d by d cross v, where d is like the size of the embedding which your network is trying to produce, and v is the size of the vocabulary. So what you can do is like you can transform like the hidden state of this vector by into this, and you end up with like v logits. So so this is like your network is trying to so you have like logits here which are equal in size to the vocabulary, and the logit corresponding to the word make is what you want to be high. Okay, so you want this logit to be high and all other logits to be low, and that will be enforced through a standard cross entropy loss. So that's how you make it work. And so you multiply like this d cross v, you multiply like the output here by a d cross v matrix. So one thing which you need to understand here is that let's say you have this input word, and this input word is a vector v. So your embedding vector, like your input embedding size was actually, you had like v words and d size, and similarly at the output you were trying to convert like the hidden state d by multiplying it by another vector which is d cross v. Okay, so if so there are 2 word matrices which are going on here. There is one word matrix which is actually converting the word how into a high dimensional vector which you are translating, which you are injecting into the neural network, which is this matrix. And then there is another matrix by which you are trying to multiply the output hidden state to actually get the logits back. So one matrix here, so one matrix at the input is of dimensionality v cross d, and one matrix at the output is of the dimensionality d cross v. So you can see that these two matrices are essentially of the same size. So what we can do is we can imagine that this is only one matrix, so there is only one weight matrix which you are trying to learn. So let's say this weight matrix has the weights w, and then the one at the output, instead of defining it to be like a separate matrix, you can actually describe it as the transpose of the matrix which you are trying to learn. So rather than learning like 2 separate weight matrices here, like one of size v cross d and one of d cross v, because that will double the memory, you can just imagine that you are learning only one matrix. One is weight and one is w transpose, and the parameters are like shared among the input and the output layers. And this is something which is known as weight tying in practice. Okay, so this is good. And let's say that you manage to train a network in such a way. Okay, so let's say that you manage to train a very beautiful neural network in such a way, and then by the end of this training you ended up with something. Let me clear this, sorry. Okay, so let's say that you manage to train it, and let's say by the end you have like this two-dimensional matrix of v size and d dimensions, and you understand like you got like this set of numbers for maybe a word corresponding to does. Okay, so now the point is like, what do you see here, like what the problem is? So there are two problems here, which are as follows. So the size of this matrix is limited to the size of the vocabulary. So if there is like some unknown word which appears in your sentence, then technically you need to like increase the size of this matrix and then learn the whole thing again, which is like generally not feasible in practice. So this is like one problem, which is handling like the unknown words. And there is second problem, which is known as let me remember it. Okay, so there is second problem here. I'm trying to find it. Okay, sorry. So I'm back and now I finally remembered what I was trying to say. So in this case, like there is another problem, which is that it assumes that for each word, so let's say for does, it assumes like for a word like does, there is always like just one vector which describes what it is. But turns out like this is like too rigid for the network. So I want to explain this to you with the help of an example. So for example, you have two sentences which say that I went to bank to withdraw money, and one is I am sitting on a river bank. So if you see here, the meaning of the word bank is actually changing depending on the context around it. So here the bank refers to an entity where you can withdraw money from, and here the bank refers to like the side of the river where you can rest. So obviously these two banks have nothing to do with each other, and somehow like you need to capture these nuances, and the word bank should actually change its context according to what is like the according to like what sentence it is about, right? So but if you assume like that you are having this sort of rigid structure where your word bank will always have just one possible value, that gets too rigid. And because this is like just one vector, you can't capture the nuances between when the bank actually appeared in the context of like the entity where you draw the money from, or when you were sitting on a river bank. So turned out that this was like a fundamental problem in word2vec. And obviously there was another issue where you could not, where like here like you're just injecting these vectors v1 v2 v3 v4, and there is no way like in which you are able to retain the ordering here, and that is like not a really good practice. And that's where like the transformer based models actually came and shined. So what they do is that the transformer is able to like inject all the input words in a certain way, and in the output like it gives you embeddings which are actually dependent on the context around them. So like for example, this how, like when it will go in, the embedding for how which you will get out is actually going to be going to be different from the embedding of the how which went in. And the point is that the embedding of how will change in accordance to like the words which are around it. And this turned out to be like a seminal paper which changed like the course of the NLP field. And this paper was originally titled BERT, and it's actually published by Google, and you can check it out, because from what I know, like sometimes the interview people ask this. Okay, so now that we have discussed this, let's talk about, so this is like, so these two architectures are how do you actually learn like the representation of the words. Now you also need to learn the representations. So this is only taking care of the text part, but you also need to learn the representation of the images or the videos, right? There needs to be some encoder which is actually looking at a given video which you uploaded, and it's able to like learn the video embedding corresponding to that. So how will that encoder actually look like in practice? So basically you have an input video, then you pre-process it, and then you have a video model, and it is converting like the video into an embedding. So the point is, what will be the design of this video encoder look like? Okay, so obviously you can imagine that you have like a encoder, and so your video model can be pretty simple. What it can be is that you can just, so if your video has let's say 10,000 frames, you can just sample let's say 10 frames on it, and then what you can do is like for each of the frame you can compute like its embedding separately. these 10 embeddings, and then finally you can combine them into like another type of, you can like just average these embeddings and try to get a new embedding, which is what you call like the video embedding. And so the architecture for that can be very simple. So the architecture for that can be pretty simple. So for example, let's say you have an input video, you pre-process it and you sample the frames, and then it goes through an image model, and the embeddings you get are finally averaged. And this is what is the video embedding here. So turns out like this type of architecture will work in practice, and its strength is that, so let's say you have an image classifier which can look at an image and then predict some embedding for it. Since you have like broken down your video into frames, you can process every frame it frame wise, and you can just repurpose your image model for video. So in that case, like you don't need to train a model separately for videos, you can just repurpose your model for the image. So since you can repurpose your image model, turns out like there is already a lot of models which are trained on large scale video datasets like ImageNet or Lion 5B, on which like the original clip model was trained, and you can just repurpose them for videos, and you can actually make good use of like whatever they have learned before, and then you can use them in the video understanding. Okay, now but like this has like several problems. One is like here like the network is not able to, so you are creating like all the frames equally, and your network has no sense of like what is time, right? Because these frames are just coming in, and there is no temporal understanding of like how the order is being encoded. But there might be some applications, for example action detection, where you are opening a door or closing a door, and if your sequence of frames like changes, like if you just reverse your frames, then the action goes from opening a door to closing the door. So obviously it becomes really important for the model to understand like what is the correct order of the frames. And there are like a few works around this which can try to inject like temporal information into the model, and you can actually look at those works and see like it's like a pretty interesting direction. But this is something which you can discuss during your system design interview. Now let's look at the model training and how will we actually train such a model. And turns out like it is pretty simple. So we have already described like how the video encoder will look, which is just a repurpose of image encoder, and the text encoder can be something which is a transformer based text encoder, or maybe a word to vec architecture. And let's say you have like a bunch of texts, and you are predicting like there is like one video and there is like a bunch of texts, and you're predicting like all the possible text, and out of these texts there is only one text which corresponds to the video description, and you can bring that closer. So if you have like this video embedding, and this is like the text embedding for the video, and there is like another embedding which is for another video, which is v dash, then what you can do is like you can try to push these together, and then you can pull these apart. And that is something which like the contrastive, which is known as contrastive learning, and you can actually do that by just taking a dot product and applying a softmax. So that's like the whole idea, and that actually allows your network to learn very useful internal representations. The next step in the system design interview is to, once you have described the model and discussed the architecture, the other part is to decide upon the metrics. So in this case, like there are three metrics. One is like the precision, one is recall, and one is like the mean reciprocal rank. So the precision is very simple. The precision is, let's say you gave it like a particular text query, and then you output like the k-sized, recommendation. So you have like video 1 here, video 2, and so on till video n, which are like your recommendations. So how do you actually know what is a good recommendation? So precision is basically that so you divide like by the k, and then you see like what are the number of relevant items among the top k items, and it turns out like that will be like a good metric. But in this case here like the problem is that so here like what the people are noting is that the numerator of the precision formula is at most 1. So for a given text query, like let's say there is only one video which matches that, then the numerator of this whole thing can be at most 1, and then it is not very helpful, because let's say let's say that if you rank like the associated video at the top of the list, and the precision at the rate is only 0.1. So that's why like precision is not a good metric, and similarly recall is also not a good metric. And what you can just talk about is something called a mean reciprocal rank. And you can, and this mean reciprocal rank is nothing but it's just that you try to calculate like the exact rank which your model has given with respect to the different inputs. Okay, so now now let's look at the online metrics. So in case of like online metrics, obviously once you have recommended your data, once you have recommended your items to a user, like what are the some sort of metrics which you can collect. And one is obviously click through rate, which is like how often did a user click on the videos which you recommended, and how well it actually like how often he clicked that. So if someone clicked at your videos in 2 times or 10 times, then you know obviously the recommendation in which the users click 10 times is actually the correct one. And then the other one is the video completion rate. So you can see, you can check, okay, out of all the recommendations you gave, what are like the some, what are like some of the videos he entirely watched. Because if he entirely watched, it means that okay, obviously he was interested and he learned something good. And in case like he left a comment, that's even better, like because he was engaged. And that is something which you can track. And then what's the total watch time? So obviously sometimes a user might not look finish the video, so in that case he might just fluctuate through the videos which were recommended. So you can track, okay, if you recommended 4 videos and he clicked on 3 of them, what is like, and he, let's say he didn't finish any of those videos, then out of those 3, like what is the total time he watched it. And that can be actually a good indicator of how is the quality of the entire video here. So this is good, but let's talk about like a limitation of our approach. So in our approach, like we have one limitation, which is that we thought that every video has a corresponding text description, and there is like a one-to-one mapping between these. So let's say there are let's say there are 2 videos of the same category. So let's say there are 2 videos. Maybe one video is dogs playing, and another video is also dogs playing. So in this case, like there can be 2 videos which have like same, which have same description, but they are visually very different, right? But they have same text. So obviously the method of contrastive learning, like this assumption doesn't hold there. And I think that is one of the key points why networks like Clip cannot perform that well, because they assume this sort of like one-to-one assumption that each video has a unique text, which might not hold true in practice. So that is like a fundamental. So whenever I see these kind of issues, I really like the word symmetry. And again, this is like a symmetry problem because the network is not learning many to one correspondence in any way, which is not correct, and it actually needs to understand that a lot better. Okay, so now once you are done, these are like the crucial, so you have like the key components, but then it is also really important to understand like the individual components in more detail. And let me just focus on, what are like the individual components. So let me try to zoom in here. Okay, so I'm sorry. Okay, so the key point is that so here like the point was that you are so you are like so the way like you structure your pipeline is generally basically so first will be like the way you will build your inventory. Okay, so let's say there is no user interacting with the system. Okay, there is no user interacting with the system, and all you have is like a bunch of videos which are trained. You have a bunch of videos and you have their text descriptions, and you want to keep a model which is trained. Okay, so this is like the video indexing pipeline. What it will do is that it will take all the possible videos, which is the new videos. So these new videos correspond to the videos which were originally used to build the algorithm, maybe when YouTube was launched, and also like the new videos which users keep uploading as the time goes by. Every day like billions of new data videos are updated. So what you can do is you can take these videos, you can pre-process it, and then you can dump like the video embeddings through the video encoder. Okay, and then similarly what you can Similarly, what you can do is like you can have a text prediction pipeline where you have the videos. You somehow like you try to get like tags out of those videos. You also try to like pass them through some sort of auto generating ML model which is trying to understand, okay, what is the video on. And then you can also like parse what are the individual texts, and you can store like all of this in your database. So like for each video and corresponding text, you have like a database which talks about, okay, what this is like the video, maybe this is the video embedding which you have pre-computed, and this is the text of like what video is on. So you can like do that, and that's true. Okay, so now so this is how like you can actually interact with your system. So this is how like you feed like new data into your pipeline. And now let us discuss like how does what happens when so these steps, like here the step 1 and the step 2 are only important when you're trying to build your database, which is what is operating behind the scenes. And now let's say that you have already built your database, and a user comes in and he gives you a query, and you're interested in knowing like how will the system flow. So obviously, as we discussed, that given a query, there are two ways to run the search. One is that you actually try to search all the possible texts of the videos in your inventory and try to see like what is happening, and whether they match it or not. And this is something which is known as the Elasticsearch. And Elasticsearch is something which allows you to carry out these searches on multiple videos in parallel, and you can actually use that, and you can get like final video recommendations which match the text. And then there is also visual search, in which like you convert like your text query into some sort of embedding, and then you have like the embeddings of the videos which you had, and then you can run a nearest neighbor service on top of it. And obviously, like if you have like if you have a billions of videos in your database, then you can't run nearest neighbors, because computing it will take a lot of time. So you can run some sort of optimized algorithm like approximate nearest neighbors, which is also I explained that in the visual search video which I originally did, and you can actually check that out. And then let's say that once you did this visual search mechanism, it also gave you like hundreds of videos. So now you have some ranking which comes from the visual search and from the text search, and you have like a fusing layer which is trying to combine these outputs, so that like finally you have like the final recommendation which you have, which is like the final recommendation you did. And then finally, like you can have some sort of re-ranking services. So like till this point, like the entire algorithm was depending on sorry, let me scroll it back. Okay, so till this time, like the entire algorithm was depending upon neural networks, and let's say you predicted some rankings, but there are some rankings which are like business driven, which a neural network can't do. So for example, sometimes so let's say it's Christmas, and your model wants to recommend most of the things which are Christmas. So then you can hard code that rule in the re-ranking pipeline, and then like whatever the business wants and like whatever the offices of people want, and then you can just re-rank the predictions which your model gave according to the business needs. And finally you can have like the correct list which you can show to the user. And obviously, if you are a UI person, you can easily do that. Okay, now so that is what this whole thing is talking about. And now, what are like some other things which you can talk about in your interview? So what you can do is that so right now in videos, like we just use the representation of the video. So like video encoder just encoded the frames, but there are additional features like video length and video popularity which are possible. And similarly, you can use like some sort of ML model, and to find like titles and tags. So like if someone has not given good description of the video, you can run the video through some sort of captioning module or something, summarization module, and you can get that information. So that's it. And then obviously there is like sometimes the interviewers tend to ask you about two other things. One is something which is known as the cold start problem, and then the second thing is like the freshness problem. So what happens is that sometimes like when you have built your database and none of your users has used it, then you don't know like what to recommend in practice since you don't have like any real information. So that's a cold start problem, because there are certain videos which are like let's say you uploaded new videos and there is no view there, right? So if there is no view there, then obviously you will not be able to uh, you will the network will say, your ranking will say, oh hey, that video has never been watched. So then how do I recommend it? It will end up never recommended it. And what will happen is that certain videos which you watch for a lot of time will be recommended more and more, and then certain videos you don't watch at all will never be recommended at all. And that's a way in which like new videos will never be updated. So how can you like change your algorithm so that like the new uploaded videos are also recommended? So maybe like you can add some sort of like time flag, and whatever are the new videos which you recommended, you can actually whatever are the new videos which you uploaded, you can actually upload them again. You can actually boost their profile, and you can actually sort of boost like how they're showing to the users, and that's a good way to get around it. So that's like the cold start and freshness problem in a gist, and it helps to actually know that in practice, because that was also one of the points where I screwed up my last interview with Amazon. Yeah, but it's good because sometimes our failures teach us what not to do. So this is like a list of all the things which you can talk about, and like whatever we have discussed. So I will not go over it again, because that is like the part of this video. And I have also highlighted some of the few. I have also highlighted some of the key papers which you can read, which are really important to understand this concept in more detail. And sometimes the interviewers do tend to go in more detail, and it will help you to like actually learn them. So that's it for me, from my end, and I hope like you like this video. And I apologize if it's too long, but I think that's because I wanted to cover a lot of content and didn't want to sacrifice the quality. Hopefully you liked it, and in case you want me to make some other video, I can go ahead and do that. And yeah, thanks for watching, and let's move on to the next video. If you like my channel, please hit subscribe and comment, because it means really a lot to me. Thank you.